Okay, let's solve 3 example problems for high frequency response. Okay, first problem, actually from these 3 problems, I think you can get how we can get the body plot. Okay, first problem is this BJT amplifier. Okay. Let me see that there's R sub S 1 kilo ohm and C sub S is 10 microfarad and R sub B 1 mega ohm and RC and the CC and RL and the CL in parallel like that. Okay. And in this problem, identify the high frequency, low frequency capacitors in the circuit. Identify. Okay. Let's see. This C sub S is frequency low C sub S problem, right? And also C sub C will be problem. Frequency high, this will be short, and this will be short. Okay. From frequency low, the CL is like open, it's not okay, but frequency high, CL will be short, and the output will be ground. So we have to consider CL in high frequency side. Low frequency, we have to consider C sub S and C sub C. Okay. Also, we have to consider internal capacitors in the BJT also. Then let's make also high frequency, low frequency body plot and find the midband gain, voltage gain at the midband. And FT is given. FT is unit gain frequency. Okay. The gain equals 1 at this frequency. It's called FT. And beta is 100. Base emitter voltage 0.7 volts. And RO is infinite. So don't worry about the early effect. And C sub mu equals 0. And base resistance Rx is 10 ohm like that. Actually 10 ohm is very small. Actually we can eliminate this one like that. Okay. To get the voltage gain, we have to know the DC current. What is the collect current? What is base current like that? This capacitor C sub S and the C sub C block the DC biasing current. So we have to consider only this circuit for collect current and base current. And right? Okay. So collect current. Okay. Collect current is maybe we can find base current. If this is a for the active mode, so base emitter voltage 0.7 is given here. Where is this 0.7 volt? This 0.7. So this 12 volts, 0.7. So voltage drop across RB is 12 minus 0.7 and divided by 1 mega ohm is base current. So we can have base current. And if this is in active mode, for the active mode, the beta times IB is collect current, we can have collect current. Okay. That's what doing in this approach. So collect current is the VCC minus V sub F minus R sub B is base current times beta is IC. So VC is 12, BF is 0.7 volts, base emitter voltage, and RB is 1 mega ohm times beta 100 is 1.13 milliampere like that. Okay. To get the voltage gain, what we know is voltage gain is simple one is minus GM times RC, right? The simple one is voltage gain is minus GM times RC. So we have to know about GM, transconductance. Okay. Transconductance is given by IC over VT. So we had IC is 1.13 milliampere. VT in this textbook is 25 millivolts. Okay. So transconductance is 45 milliampere per volt. And also you can get the R pi between base and the emitter resistance. R pi is beta divided by transconductance GM is beta 100. R pi GM is 45 milliampere per volt. So R pi is about 2.2 kilo ohm. Okay. In high frequency case, an internal capacitance C pi is given by this formula. C pi. C pi is between base and the emitter capacitance. C pi is Gm of 2 pi Ft. Ft is transient frequency. It's when the frequency, this frequency is voltage gain is 1 case, minus C pi. In here, put the C pi equals 0 here. C pi is 0. So this is 0. So Gm over 2 pi Ft. Ft is 450 megahertz. So C pi is about 16 picofarad. Okay. So we need this C pi for high frequency case. Okay. We have to draw equivalent circuit for first low frequency case. Okay. Low frequency case. We have to consider this guy, low frequency case. Okay. Impedance is 1 over J omega C. And the low frequency, we have to consider this one. And okay, low frequency, this is impedance so high, we can ignore this one. Okay. So in the BJT equivalent circuit, then we have this is BJT equivalent circuit, and immediately connect to the ground. Okay. And the base side, there's Rx in the base resistance, Rx, actually we can ignore that. Actually. Then we have a RB, CS, RS in parallel. Okay. See, this RB parallel ground, and CS, RS, then ground. Right? So upper side, we have RC, ground, and CC, and RL. Okay? See, upper side. And from here, RC, ground. Then CC, and RL, ground right there. That is, this is equivalent circuit. Okay. So input is here, and output is on here. So output voltage is I out through this RL. I out times RL, 1 mega ohm is output voltage. So we have to go to, first, we have to go to V in, to the this one, VX like this, VB. Then we have to go to V pi. If we ignore this R sub X, this is VB, this VB. This VB equals V pi. So we have to go to VI to the VB, VB to the V out like this. Okay, we need 2 steps like that. Let's find the VB. And the VB to the V in. Okay. VB is V in. V in is applied across RS and the CS. And then this RB and alpha in parallel like this. But VB is just cross alpha. And but this RB and alpha, they are in parallel like that. Okay, so again, V in is applied from here to ground. VB is from here to ground. Here means this one and this in parallel. So VB is V in times the total impedance from here to ground is RB parallel to the alpha. Ignore this one, okay? RB alpha is parallel. And plus this one is 1 over J omega CS plus RS. And the VB is applied from just from here to here is RB and alpha in parallel. There. No problem, right? So as shown here, alpha RX, maybe ignore this one. This is small. And alpha is about 2 kilo ohm. RB is 10 ohm. You can ignore this one, small, ignore. And RB paired with the RX alpha. RB is 1 mega ohm. Alpha is about 2 kilo ohm. So this is almost alpha. You can ignore this one, ignore this one. So R pi. So we can simplify using this one. So B pi. Okay. Again. So in the numerator is maybe R pi. Okay. In parallel case, we can ignore big one. This is gone. So we'll have R pi. And here is R pi. Right there. And again, this PB and the P pi is same because if we ignore this Rx 10 ohm, so P pi and the PB is almost same, and the PB is this one. PB is this one. PB is B in times this is numerator is R pi, and denominator is this is R pi, and this RS, this is 1 over J omega CS. Like that. Then we have to play this game to make this kind of form. Okay, in denominator should be 1 plus J omega C, like that. So we can have make this way. And we can take out this R pi plus RS and R pi take out. So we'll have this form. Okay. Okay. Output voltage. Again, output voltage is this output current I out times RL is output. Okay. So we have to know I out. I out is this is GMP pi, and the current split. The current this way and this way to split. So current to I out is we have to multiply this R sub C. Okay. So I out times RL is B out. Okay, the current is GMV pi times okay RC over total impedance. This guy and this one like that. So RC plus RL plus this capacitance impedance 1 over J omega CC. This is I out times RL. Okay. It's a current divide term. Okay? And then we just modify this, make this form minus GM RC RL over RL plus RC. Okay, see, you can see this one is if we have just RC and RL like that, this is the voltage, output voltage like that. This one, right? And V pi. Just V pi, we just substitute V pi here. So we can have V out and V in. Okay? So we can get the voltage again. So V out over V in is, that means gain is minus GMRC times these two terms. Okay? And then modify this one, we'll have this way. Minus GMRC, R pi over R pi plus RS, RL over RL plus RC. Then these two terms, 1 by the C sub S, 1 by C sub C, like this. It is not difficult, okay? See what we can see from here. This minus GMRC is like see, this gain is minus GMRC, right? Voltage gain of this one minus GMRC is from here. Okay. This one, R pi over R pi plus RS is if we have RS there, like that is, let me draw that. If we have RS, and then BCC, B out, B in, R sub S, like that. Then because there's voltage drop across RS, we have to have this term. This term. And this term is if we have this is RC, if we have RL here. Yeah. Like that. Okay. From here, what we can see, okay, what we can see is, okay, if alpine plus RS, okay, if this term is like 1 plus J1, okay, if this is 1, and if this is 1, okay, then the gain will be reduced by 1 of square root of 2 in amplitude, that frequency. So this should be 1, and this should be 1 like that. Okay. So F1 is, okay, this one. Okay. If we plug in T sub S, R pi RS will be 5 Hertz. And if we put the CC and this RC, RL will be 0.016 Hertz like that. Okay. Okay. How we can get this one is maybe we'll get the shortcut later on. Maybe let's see shortcut, how we can get the shortcut. Okay. In low frequency side, and series one is important. Okay. Series, like this one, series one is important because frequency low, it bothers that. That's big attenuation because impedance so high attenuation. So what is series with this C-series? On this side, RS. On this side is like RB and R pi in parallel, but RB is so big, so R pi. So C-series times RS plus R pi. Okay, that's shown. See here. C-series times R pi plus R sub S. So frequency we put 2 pi, omega of 2 pi. 2 pi times C sub S, then multiply R pi plus R sub S. How about this one? CC case. Frequency low, this CC impedance so high, it bothers. So we have to consider CC at low frequency case. What is the impedance on this side? RC. What is on this side? RL. So CC times RC plus RL is this one. Okay, just plug in RC and RL. We have 0.016 Hertz. Okay. So this gain will be reduced, attenuate by at F1, and then again attenuate at F2 like that. Actually, this will be attenuated by minus 20 dB per decade. This will be minus 40 dB per decade like that. Okay, we'll have that answer later on. Okay, so we did for low frequency side. Okay, let's see the high frequency side. High frequency case, we have to put a device capacitance like C pi. C pi is between base and emitter. C pi, we got C pi value, 16 picofarad. Okay, frequency high, that high frequency case, see, frequency high, this is kind of short, right? So you can ignore that in short. Frequency high, this is ignored, short. But this bothers that because the signal go through this CL, go to the ground. So we have to consider CL at high frequency side. Okay. Also, if we have a C pi here, C pi here, we have to consider this C pi. Anything like a parallel to the signal, we have to consider that for high frequency side. And this series one, we have to consider low frequency side because impedance is so high. Okay. So maybe we can solve this problem again like this, but actually we can get shortcut, but we'll do later on. Okay. The voltage at this point is given by this expression. Okay. Okay. This V phi is V Thevenin's times how much go to here. Okay. How much go to here. And across here on all of this one plus this. Okay. RP is this one parallel with this guy. That. And the V pi is given by this expression in terms of V in, V pi. Then we can have V out. Okay. So V out is this current times, okay, all this impedance, right? All the RC, RL, impedance CL, they are all in parallel. They are all parallel, see? Minus V pi, all parallel like that. RC, RL, impedance of CL, they are in parallel. So we can have like this. So now we can have a V out, a V in, voltage gain is given by this expression. So try to make in denominator 1 plus j omega, something like that. This by C pi, this by CL. Okay. Again, this is minus GM RC1L is just by the RC-RL in parallel case. And R pi plus RS is, we have RS in the input side there. So we have to have that. And this is the same for the low friction case. Actually, this is a midband gain like that. Yeah. So F3 to make this one, this make 1 plus J1 and 1 plus J1, that. Okay. This to be 1. That frequency is, just put all these numbers, we'll have 2.2 megahertz. F4, this become 1 is 14.5 megahertz. Okay. Okay. So overall gain, midband gain is this guy, this midband gain. As shown here, GMRC is just BJT, midband gain. And this is input side because R sub S. And this is output side because RL. Okay. RC and RL like that. So gain is about minus 157, this midband. Okay, so in midband, gain is 157, negative 157. This is 44 decibel. And we try to put F1. and F2 right there, and F3 high frequency side, and F4 high frequency side. Okay, then we can make very simple ways like fibers from F1, F3 like this. I can write this way, maybe like that. And F3, F1 is make a straight line like that. Then this should be 20 dB per decade. And this is 40 dB per decade, slope like that, okay? And to make a smooth curve, maybe this is maybe 1, and this is 1 of square root of 2, actually minus 3 dB points. This point and this point, minus 3 dB point. This is minus 3 dB point, make a smooth curve through this minus 3 dB points. Same way, and F3, 2.24 megahertz, just past this point. This point is minus 3 dB below than this corner. So you make a smooth curve past this one. And then this way also. This minus 40 dB per decade like this. So actually the bandwidth is not this one. Bandwidth is not F3 minus F1. If we have this F2 and this will be pushed down, this will be more, down a little bit more. This F3 pushed down a little bit more. So how we can calculate the FL and FH is, FL is we have to add these two numbers down more like this. F1 plus F2 is FL. Okay. Where is that stop? Okay, I do not see here. Okay, maybe we'll see that later on. Some other problem. Okay, so in this case, like FL is F1 plus F2. And FH, so this will be a little bit higher then, maybe around here, very close here, because this 0.016 adding to 5 hertz is almost same, not much change. FH, this one is, this FH is F3 parallel with F4. So it will be down just below. So between here to here is bandwidth. Okay? Bandwidth is, let's say this guy's in triangle, this square. Okay. Triangle minus square is bandwidth. So bandwidth is not F3 minus F1. Okay. So high frequency side will be lower than F3, low frequency side will be higher than F1. So this is bandwidth. Okay. Let me go back again. Okay. If you understand this problem, and you can see most of this bandwidth problem, high frequency response problem, and in this very good example problem. Yeah. First, in this problem, try to find the gain. We have to find current, collect current, like collect current, right? Because collect current can give us transconductor GM. So voltage gain is minus GM times RC for simple BJT circuit. So we have to know about IC. How we can get IC in this problem? We can get base current from here. If this is forward active mode for amplifier, it should be forward active mode. So base emitter voltage is about 0.7. So this 12 minus 0.7 divided by 1 megahertz base current. This base current times beta 100 is collect current. So we can have collect current. So most of this kind of problem, you don't need to justify this is active mode, because if this is amplifier, it should be active mode, normal mode or forward active mode. Okay. So then we have to consider in low frequency side, this series one is problem. The impedance so high. All the signal will be attenuated at the C sub S and or C sub C. So we have to consider C sub S and C sub C for low frequency side poles. Okay. So how we can get is like, maybe I can say this as FL1 and FL2 like that. And 1 over 2 pi CS. What is impedance on the left hand side? R sub S. In series, what is on the right hand side? And RB, alpha impedance. RB, alpha impedance. But RB is so high, so this is 1 over 2 pi CS RS plus alpha, like that. And FL2, 1 over 2 pi and CL, I'm sorry, CC. And what is the series with this one? This way RC, this way RNet, RC plus RNet. Okay. And the frequency low, the CL is open. Impedance so high, we can ignore that. It's open circuit. So we have to only consider RC and RL. Okay. And the frequency, high frequency case like FH1 and FH2. FH1 is by C pi. There's C pi is internal impedance in there. Okay. I'm sorry, C pi, like that. And what is the series with this one? Series with this one, R sub S, this side, this R pi. But this one, RC, RL, the impedance. That is what we had here, right? See, F1 is the CS, series with R pi and RS, CC paired with RC and RL, and high frequency side, CL is paired with the CIS, RC and RL, C pi paired with the, all other things. Okay, R pi is many things. Okay, RB and RS, that kind of stuff. R pi. All right. So you can have a midband gain is this midband gain. Okay. Without RB and RL or RC like this one. And this is by RS, this by RL, and this is midband. Okay. So this should be same for low frequency side, high frequency side, it should be same. Okay. Then just plot this body plot like this with a band straight line. And F1, put F2, make straight line, 40 dB, 20 dB, decaying. Then F3, F4, 20, 40 dB per decade like this. Then make smooth curve, just pass minus 3 dB point, minus 3 dB point, minus 3 dB point, and minus 3 dB point. Just make smooth curve like that. Okay, something like that. Then bandwidth is like low frequency case. This Fn, F2 should be added. High frequency case, F3 and F4, they are in parallel. So this value is slightly less than F3 around here. So bandwidth is this FH minus FL is bandwidth. Okay. Looks like quite complicated, but it's not. Okay. If you practice this problem a couple of times, okay, even you close eyes, you can solve this problem. So when you drive car, so when you see the red signal or your front car stop, you can stop immediately, right? You don't think about how do I have to stop or not, just automatically. If we solve this problem, I think a few times, this automatic problem, okay? It's not difficult, not complicated. So you will see this similar problem on the final exam. Okay, next problem. Okay, this is FET problem. Okay. This input signal and output voltage coming out from here. Okay, RS, here is another RS, and input go to the RS, and R1 and R2 in biasing registers, and RD and RL and CL like that. So low frequency case, we have to consider C1 and C2. High frequency case, we have to consider CL, and also we have to consider internal capacitor in the device, in the FET. Okay. If we ignore this in the midband, we can ignore these capacitors. So P out or P in is like minus GM times this RC or RL, RD, RL, RO in parallel, right? If RO is so high, we can ignore this one, RD parallel with RL. And how much voltage will go to from P in to the gate here is we have to consider RS. So this RG is R1, R2 in parallel, divided by RG plus RS. Okay. This R1 is 1 mega, R2 is 1 mega. The parallel is 500 kilo ohms, and RS 10 kilo ohm. So we can ignore this R1 and R2. Okay. So we can ignore this guy. So output voltage is also ignore this RO. If R is so large, ignore this one. So it's minus GM, RD, RL in parallel like that, approximately. Gain is negative 6.7. Again, this FET gain is quite low, 3 to 5, 6 like that. And the PJT gain is 50, 100, 150, something very high. See what we had in this case. This case we had 157 gain, but here FET, the gain is like 6 like that. So when you had the problem with the FET, gain is like 150 like that, there's something wrong. You have to check one more time. And also like that. So in general, the MOSFET gain is quite low. Okay, let's find. So we don't need to solve this problem again, okay? Just how we can get this F1 or F2 or FL1, FL2. Like let's say this FL1, this by FL2, because frequency low, this bothers, right? Impedance so high, a lot of attenuation by CC1, a lot of attenuation by CC2, will have very small output voltage like that. And frequency low, we have to consider C1 and C2 like this. So as shown here. And F1, like FL1 is C1 times, what is the series with the C1? Like RS and RG. On this side, RS, this side is RG. Okay, RG is actually R1, R2 in parallel, this RG. Okay, so put RG, RS, and RG. RG is again 500 kilohertz. This 10 kilohertz is 510 kilohertz. So F1 is 0.03 hertz. F2, what is the series with F2? We have to think series F2. What is it? This way, RD. This way, RL. Actually, there's RO there, but if we ignore RO, okay? Said RO is 100 kilo, but this 5K, 10K, so we can ignore this RO. So C2 times RL plus RL, RD plus RL, okay? So 1 over 2 pi times this in denominator C2 and RL plus RL, RD plus RL is 1.1 Hertz. So we have like FL1, FL2 like this. And high frequency case, we have to use in the device capacitors like that. There's some capacitance between gate and source to drain like this. So we have to consider that. And gate source is like here given 8 picofarad. Okay. And so this is power step, right? Frequency high, make short like that, short. So okay. By CDS, what is in parallel with this? We have actual CDS here between gate and source CDS. What is parallel with this one? This guy and this one in parallel. RS, RG in parallel, right? So RS is 10K, this 500K, about 9.8K. How about this? CL. Okay, CL is here. What is parallel with this one? Parallel with this one. This is parallel, this parallel, right? So C 2 pi CL times parallel this one. RD, RL parallel, RO and parallel. If this is too high, you can ignore this one. Just keep this one. We have this one. So we have two high frequency side, two low frequency side. We have that. So we can have bandwidth from this one. Okay. I think this is the last problem. And in this case, we have a CE, emitter degenerate capacitor. Okay. CE is there. Usually CE is quite large. Okay. To get all AC is going to go through here. Okay. So in DC, we have to consider this one, DC, to get the collector current. Looks like this problem, IC is given, IC 1 milliamp. If we have IC, we don't need to consider about this solving this biasing problem. Okay. So we have a transconductance, GM with IC over BT, we can have a transconductance. Okay, beta is given, FT, okay. Transit frequency, at this frequency, voltage gain is 1. Okay. And here C mu equals 0, Rx 10 we can ignore that. Okay. So using P pi, PF is 0.7 volt, this 0.7 volt. And our R is infinite. Ignore that. Okay, let's try to get the, here is to get voltage gain to find GM, ISO-BT, R pi, beta over GM, that. And C pi is given this formula. And GM of 2 pi FT minus C mu. And here said C mu is 0. C mu is between base and collector. And C pi is 14 picofarad. So first, in the low frequency case, if for CS frequency in low, this is trouble. So we have to see what is the series with the C sub S. On this side, RS. Okay, this side, RS. And the series of this one, this side, all this in parallel. All this one. Okay. So RB and R pi, they are in parallel. You know this one. This is two parallel. So Fs by this C sub S, 1 of 2 pi C sub S times this one plus this one. This is RS. This side is this two are in parallel. 26 hertz. And by this one, CE. And we have to see what is, and this is a kind of parallel type signal going to down this way. So what is parallel with this guy? This one, and this is, and this one, and this is parallel, right? So Ali parallel with this guy. And so this is R pi, you know this one, R pi, and plus this one. This is RS and RB in parallel. RS, RB parallel. And then this base side, we have to divide by beta plus 1. If we see impedance on base side, we have to divide by beta plus 1. Again, if base current is 1, collector current beta, emitter current beta plus 1. So voltage drop, emitter side is beta plus 1. If the reference emitter base, we have to divide by beta plus 1. So we have F of V is 48 hertz. And high frequency case, so FL is add this two. FL1 and FL2 add this one, 74 hertz. And high frequency case, we have to put C pi, base to emitter C pi. You calculate C pi already. And also this series one or parallel one, we have to consider. Okay, what is parallel with C pi? This guy, and this one is parallel, right? So R pi and this parallel, okay? And we'll have 17.6 megahertz. How about this one? What is parallel with this one? CM parallel with RC and RM, okay? This one. Actually, with RC, RM2 in parallel right there. Then we get this 8 megahertz. And FH is parallel with this. F pi parallel with FM is like this. See? This 8 megahertz, this 17.6, this lower than this 8 megahertz. So we can plot. So we can plot, right? We can plot like this. Something like that. Like this FL1, FL2, FC1, FH2, like that. And this midband gain, connect this one, 20 dB per decade, 40 dB per decade, 20 dB, 40 dB decade. Then make smooth curve just below 3 dB below this one at corner like that. And we make a curve like this. That. So bandwidth is not this one. Okay, bandwidth FL1 plus FL2 is maybe around here. This is parallel, slightly below that. This is bandwidth. Okay, next week we'll have final exam. So this Thursday, we'll have an online lecture. Okay, we'll talk about the final exam. And I'll point out what you have to prepare for final exam. So our class is 10 a.m. Okay, I'll send you the the ID number again, Zoom ID number again, meeting ID number by email again. Okay. See you on Thursday, 10 a.m. Okay, bye.